Welcome to NPTEL online course on fractal and multifractals. So, in the second part of this course, we are discussing the dimension theory, in which in the last classes we have discussed the fractal dimension of an object, whereas fractal is defined by mean of topological dimension and Hausdorff dimensions. We need to define and know what is the topological dimension and Hausdorff dimensions. So, in the upcoming classes we have discussed topological dimension and Hausdorff dimensions. So, in this lecture particularly we are going to discuss about the topological dimension. Topological dimensions, there are different methods are available, there are different topological dimensions available. So, in this course we are going to discuss the topological dimension in the sense of Menger-Urysohn's dimensions. Here, suppose that K is a subset of R power n. We are taking more precisely R power n. The topological dimension of K denoted as dimension Tk, that means topological dimension of K is inductively defined as follows. Topological dimension of empty set is -1. Second one, the topological dimension of K at a point P belongs to K is less than or equal to n, written as topological dimension of K is less than or equal to n if there exists arbitrary small neighborhood of P, whose boundary have topological dimension at most n minus 1. Third, K has topological dimension at most n if it has topological dimension at most n at each of its point P. That means K has the topological dimension at most n if and only if topological dimension of K at each point is less than or equal to n for all P belongs to K. In addition, topological dimension of K equal to infinity if 2 does not hold for any n. This condition 2 is not hold for any n belongs to natural number, then we can say the topological dimension of K is infinity. And topological dimension of K equal to infinity if in the condition 3 does not hold for any n. For any arbitrary small neighborhood of n at each point of P, it does not hold. For there exists n, if each point it does not hold this inequality, then we can say the topological dimension of K is infinity. So, here what is the difference between previously defined fractal dimension? For the fractal dimension, for finding the fractal dimension of the object K in any compact subset of space X, metric space X comma D, we are finding the number of minimum covering and finding the ratio how the box containing dimension measures, thus the asymptotic growth rate of the number of boxes of size epsilon needed to cover the set K. Means in the box counting dimension, the box counting dimension of K is defined as the asymptotic growth rate of the number of boxes of size epsilon needed to cover the set K. Here we are defining the topological dimension of the set K. That means topological dimension measures how many times you must take boundary of arbitrary small neighborhood before the local structure reduces to nothing. That means it is recursively reducing to empty set, eventually reducing to empty set. How many times? We will see this through the examples. Before that, this is the pictorial representation of topological dimension. Suppose if you have the empty set, nothing inside the box, then this topological dimension is minus 1. Minus 1 is the topological dimension. Then topological dimension of k, that means topological dimension at a point, topological dimension of k is less than or equal to n if there exists arbitrary small neighborhood of P whose boundary has topological dimension at n minus 1. Then we can say the topological dimension of k is at most n. This is u1, u2, that boundary of the small neighborhood of the P. Then you can find the boundary of this u1 and boundary of u2. If they have any small neighborhood, have the dimension n minus 1, then the topological dimension of k is n. The dimension of the set, if topological dimension of k is less than or equal to n, then for at every point has the topological dimension less than or equal to n, then we can say the topological dimension is n. If 1, 2 is not hold, we can say the topological dimension is infinity, as well as the 3 is not hold also, we can say the topological dimension is infinity. Now you can see here, this is the empty set, it has the topological dimension minus 1 here. Suppose you have the point here, a point, boundary are minus 1 dimensional, that means only the empty set is the boundary. If you are taking any finite or countable set, the boundaries are only the point empty set, therefore their topological dimension is minus 1, 0 dimensional space. That means boundaries are 0 dimensional, that means finite set of points. When the boundaries become the boundary, if you have the curve, you can find the boundary, the mu1, u1 and u2. The boundaries are this one, the point set. So their topological dimension is 0, therefore the topological dimension of this curve is like a topological dimension is 1. Now come to the solids, that means the disk in R power 2, boundaries are 1 dimensional curve, therefore the dimension is 2. You can get the, this is the region, the square, filled square. Then a disk region in R power 2 dimension 2, because if you are taking the disk, that you are getting the boundary like this one, the boundaries are lines in that are this kind of lines, they have the topological dimension 1, therefore the R power 2, this disk has the topological dimension 2. Similarly in R power 3, you can take any object, you can cover by the surfaces, the surface dimension is 2, therefore this cubes the dimension is 3. So though it says that no matter how small the neighborhood, the boundary has arbitrarily large dimension. No matter how small the neighborhood, the boundary has arbitrary large dimension, then the topological dimension of the object, we can call it as infinity. So here it is the defining the topological dimension of an object. To have an dimension n at less than or equal to n at a point P, we can zoom in on P by taking smaller and smaller neighborhood. The shape of the boundary should look at most n minus 1 dimensional. In R power n, we always have the topological dimension of object lies between minus 1 to n, unless that k equal to infinity. Fine. So that means the topological dimension measure how many, you can see the boundaries here, here to here. If you are taking this time, after 3 steps, their boundary tends to nothing, that means empty step. That means the topological dimension measure how many times you must take the boundary of arbitrary small neighborhood before the local structure reduced to the empty set. Simple. Now in the real line R, we will discuss the topological dimension of any real line R. So what is the topological dimension of R? It is equal to 1. How it becomes 1? you can take any point, the real number, you can take any point P on the real number here, then the neighborhood of this real number is given by P minus epsilon P plus epsilon. This is the open interval, P minus epsilon P plus epsilon will give the neighborhood of this one. Then the boundary of this neighborhood P minus epsilon comma P plus epsilon is a 2-point set P minus epsilon comma P plus epsilon. Only these 2 points are the boundary. So, the boundaries are finite set. So, the finite set has the topological dimension 0. Therefore, the dimension of the real number we can say it is as a 1. Then now the question is how we are saying the dimension of the finite set is 0. We can take any set, maybe in the R power n, in the R we can take any k equal to finite set. It has the P1, P2 up to P m number of elements, only finite number of elements consider. Now I am defining the delta as find the distance between any pair of elements here, all the pair of elements, find the distance between Pi minus P. You can take an element P belongs to this set K and find the distance between this P with all the number, take the minimum among all I. Note that this Pi not equal to P. Then the distance between any two distinct points is always greater than 0. This distance delta is always greater than 0. Now we can define the neighborhood mu of this P with the radius R, with here R is R greater than 0 and less than delta by 2. Then one can understand this neighborhood has only the set P, that means the U intersection K is only the set P. So the boundary is empty. This is the only set, only element which is in the available in the boundary which intersect with K is the only one set. The boundary is empty. Therefore, the empty set dimension of empty set is minus 1. Therefore, the dimension of finite set is 0. So, dimension of the finite set is 0. That means here the boundary is finite set. This boundary has dimension 0. Therefore, the dimension of real number is 1. That means it boundary takes one step to reduce to the empty set. That is all. Now, in R power 2 we can consider, in the R power 2 we can consider R power 2. A topological dimension of R power 2 is 2. That means we can take any neighborhood. If you are taking point in R power 2 here, any point you can take. There are its boundary is a circle. That means we can take the epsilon radius, we can make a circle like this one. This is epsilon, this is our point P. Then this boundary includes the point, this one. The circle, this is the circle is the boundary is a circle, because we take the neighborhood with distance ball of P comma epsilon is defined at set of point y such that distance between P and y is less than or equal to epsilon, less than or equal to epsilon. We are taking the disk actually. So, its boundary is a circle. So, circle is nothing but line, it has the topological dimension 1. So, boundary has the topological dimension 1. Therefore, the topological dimension of R power 2 is 2. Likewise, similarly, instead of the circle, if you are taking the point P here, one can cover by the box also. One can cover this element p by box also. Again this box has the lines, the square, it is the line, it has the topological dimension 1, therefore we can conclude that topological dimension of the any point in r power 2 is 2, therefore the topological dimension of r power 2 is 2. Now the topological dimension of r power 3 is 3. That means if we prove this one, maybe in the inductive manner we can say that the topological dimension of T r power m is m. Topological dimension r power is m. A typical neighborhood for a point P belongs to r power 3 can be taken either as an open ball or an open cube P comma epsilon. For the ball argument, for if you are going the ball argument, the boundary is, if you are taking the sphere, the boundary is the s power 2, that means the disk, which has the topological dimension 2. Therefore, this P at the point P, it has the dimension 3 at every point, therefore the topological dimension of r power 3 is 3. Like similar argument with this disk. Then if you are consider the point with respect to this neighborhood open cube, that means if you are taking the P, the open neighborhood with respect to cube is defined like this one, P1 minus epsilon. That means the cube, if you are taking the point here, the cube in the space we can consider this is the cube we will get. If you are taking the point here P, then P1 minus epsilon, P1 plus epsilon cross P2 minus epsilon and P2 plus epsilon cross P3 minus epsilon P3 plus epsilon, this forms the cube. Then it has the neighborhood as the boundary of this cube. If you are taking this cube, the boundary of the cube consider 6 spaces, 1, 2, 3, 4, the 5 and this one 6 spaces. Each spaces is nothing but a filled square, not a filled square. Each space is 2 dimensional and their union is still 2 dimensional. If you are taking 6 spaces union, still 2 dimensional. Hence, in both the cases the boundary is 2 dimensional. This case also 2 dimensional, this case also boundary as 2 dimensional. Therefore, the topological dimension of r power 3 is 2. Here we are taking this one, this has the boundary like this one. If you are taking any point P in this cube, it has the boundary like this one. Now, this has the dimension 2, topological dimension, therefore, this has the dimension 3. For proving this one, this topological dimension, we are taking any point P here and find the open neighborhood. This is a filled square, this is a filled square. If this boundary is just a square, that means the lines, this has the dimension is 1. Why this has the dimension 1? If you are taking any point here, here on the line, then it has the boundary like this one, the interval, this interval, it has the line interval. So, this has the dimension 0 because this boundary is empty set, this boundary is the finite set, empty set, it has the dimension minus 1. Therefore, this has the dimension 0. If this has the dimension 0, this has dimension 1. If this has the dimension 1, this has dimension 2. If this has dimension 2, this has dimension 3. So, the topological dimension measure how many times you must pass to boundaries of arbitrary small neighborhood of the point P before the structure become the trivial, nothing, it takes 3 times. Therefore, the topological dimension of r power 3 is 3. In general, you can say the topological dimension of r power m is m. Now, so these are all the classical, the Euclidean on the spaces r power 2, r power 3. Now, we will go in more precisely. Take the Cantor set. the Cantor set is contained in R. The topological dimension of R is, the topological dimension of R is, just now we come across the topological dimension of K is 1, R is 1. Now let take P belongs to a set C and consider arbitrary small neighborhood P with the radius epsilon. The intersection of this ball neighborhood and the set C is totally disconnected set, because the C does not have any interval. The boundary consisting of at most finitely many points. Therefore, the topological dimension of the boundary intersection is less than or equal to C, which implies the topological dimension of Cantor set is 0. This is the simplest way verifying the topological dimension of the Cantor set is 0. If the topological dimension of the Cantor set 0, whereas it is embedded in an R, it has the topological dimension 1. It has the topological dimension 1. And also note down, we already completed what is the box counting dimension of the Cantor set. It is ln 2 by ln 3 box counting dimension. So, the topological dimension of Cantor set, it is strictly less than the fractal dimension, that means the box counting dimension of the Cantor set C. Fine. So, as per the definition of Professor Mandelbrot, he mentioned that if the Hausdorff Biscoff dimension it exceeds the topological dimension, the object is called the fractal. But now the particular case of the Hausdorff dimension, we discuss the fractal dimensions. So, if the fractal dimension, that means the box counting dimension exceeds the topological dimension, so it shows that, once again assures that C is a fractal object. Now, we will come for the Sierpinski triangle. Now, consider the Sierpinski triangle, which is a subset of R power 2. If you are taking an element P in S and consisting of small neighborhood mu epsilon of P, the intersection of mu epsilon of P, that means the neighborhood of P at the radius epsilon intersection S, form a network of line segment. So, how we obtain the Sierpinski triangle? This is Sierpinski triangle. After this is the first step, we need to divide two equal part, line joining the point, then again divide as half of the three sub triangle, then we are getting like this one. Now, you can see the intersection of any point if you are taking, and the neighborhood and the S forms the network of line segments. It is a line segments. The boundary consisting of finitely many vertices. That means the points containing the finitely many vertices. So, it has the dimension, the boundary has dimension 0. So, here the finite set, the boundary yes, in the Cantor set the boundary consists of at most finitely many points. So, finite point dimension is 0. Here the dimension of finitely many vertices, then the boundary of this one intersection S is less than or equal to 0, then the top dimension of the Sierpinski triangle at any point is less than or equal to 1. Therefore, the Sierpinski triangle, the box counting dimension is 1, whereas if you consider here for any point, if you are taking any point, their dimension is 0. Therefore, the Cantor set dimension is 0. Here we are taking any point, the set S has the dimension 1. Therefore, the topological dimension of the Sierpinski triangle is 1. Now the same argument for the Van Koch curve. Let P belongs to K at any point in the Van Koch curve, form the neighborhood. the intersection between this one is a highly oscillating curve segment, because we are using this type of structure is the first step. Then after the first step we are getting here and like this type of structure. So, if the intersection of this neighborhood and K is a highly oscillatory curve segments, the boundary reduced to the endpoint type structures, therefore, the boundary has dimension 0, the boundary has a dimension 0, therefore, the dimension of the van Koch curve is equal to 1. So, note down here the box counting dimension of the set S, that means the Sierpinski triangle is ln 4 by ln 3 by ln 2. So, which is greater than 1, their topological dimension is 1. And similarly, here it has ln the box counting dimension of the Koch curve is ln 4 by ln 3, which is also greater than 1. The topological dimension is lesser than the fractal dimensions, and alternatively the fractal dimension exceeds the topological dimension. Therefore, the van Koch curve and the Sierpinski triangle also in the Cantor set they have the fractal nature. So, these objects have the topological dimension is lesser than the fractal dimension. Therefore, these 3 objects considered as the fractal structure as per the definition given by the Rosen-Mandelbrot in term of dimension theory. Now, here this topological dimension we defined through its boundaries. We are finding the any point and we are checking the arbitrary small neighborhood of the point, then their dimension, based on their dimension we are finding the dimension of an object. Now, we need to move on the Hausdorff dimension, then thereby we are comparing the what is the difference between Hausdorff dimension and the fractal dimension, and when both are equal, and how to define fractal in term of dimension theory by using the Hausdorff dimension and the topological dimension. We will discuss in the next lecture. Thank you. So, one can refer these books for more further references. Thank you.